Hello students, today we shall see what is double integral as the limit of a sum and how to calculate double integral as repeated integrals. So double integral as the limit of a sum. Let us see the definition. Let f of xy be a bounded function of two variables x and y defined at each point x comma y, first bracket x comma y, in a bounded region capital D of the xy plane, and let capital D is divided into n subregions d1 d2 dn with respective areas delta a1 delta a2 delta an, and let first bracket xr comma yr be any point in dr, that is in the rth subregion dr, for all r equal to 1 to 3 n. That is, we are taking one point from each of the subregions, x1 yn from d1, x2 y2 from d2 xn yn from dn. Then the limit of the summation f of xr comma yr into delta ar, function value into area of the subregion, summation r from 1 to n, as n tends to infinity. Limit of this sum as n tends to infinity, number of subdivisions tends to infinity, and simultaneously largest of delta ar tends to 0, means every division is very small, area of every division tends to 0. If largest one tends to 0, so everyone will tend to 0. Yes, so limit of this sum as n tends to infinity and simultaneously largest of delta ar tends to 0, if it exists, is called the double integral of the function f over the region D, and is denoted by this symbol, double integral symbol. Below we write capital D, that is integral is over the region D f of xy dx dy, or this symbol double integral over D f of xy dA, dx dy is dA symbol, elementary area. So this is definition of double integral as the limit of a sum over a bounded region for a bounded function. Thus, in the note we write it in short: double integral f of xy dx dy over the region D is equal to limit as n tends to infinity summation f of xr yr delta ar, r from 1 to n, where of course the largest of delta ar tends to 0. In particular, if f of xy equal to 1, f of xy equal to 1, function is 1 at every point for all xy in the domain D or region D, then this double integral of the function f of xy over D becomes limit n tends to infinity summation delta arr from 1 to n, means it is just sum of the areas of the subregions, that is equal to total area of the region D. So when the function, rather integrand, is 1, the double integral gives area of the region over which we take the double integral. Also, if f of xy is considered as density, mass per unit area, at the point x comma y, first bracket x comma y, of a region D, then the double integral, this symbol double integral f of xy dx dy over the region D, gives the total mass of the region D. F of xr yr is density, delta r is area, so density into area gives mass, and this is the sum of masses of the subregions, so it gives the total mass. So double integral gives the total mass, physical meaning you can say. Now how to calculate double integral in Cartesian coordinates, of course. Calculation of double integral as repeated integrals, let us see. If f of xy is a continuous function of x and y in a bounded region D of xy plane, and capital D is bounded by continuous curves y equal to phi of x, comma y equal to psi of x, and the lines x equal to a and x equal to b, where a less than b, and also phi of x less than or equal to psi of x for all x in this interval, a less than or equal to x less than or equal to b. When x varies from a to b, our phi x is always less than or equal to psi x, that is y equal to phi x curve is below the y equal to psi x curve. One curve is below, one curve is above. So the region should have a particular shape. If the shape of the region is like that, rather boundaries are like that, two curves above and below and two straight lines to the left and to the right, in that case the double integral f of xy over the region D, double integral of f of xy over the region D is given by this repeated integral. First we integrate with respect to y. Integration f of xy with respect to y from y equal to phi x to y equal to psi x, and then we integrate with respect to x from x equal to a to x equal to b. The idea is that take a thin strip from y equal to phi x to y equal to psi x. See in the figure it is thin strip. So along this strip x is constant. So when we integrate f of xi with respect to y, we assume x constant. We can call it partial integral. F of xy with respect to y we integrate means keeping x constant, as if in partial derivative when we differentiate with respect to y we keep x constant. Here we integrate with respect to y, so we keep x constant. So x constant means it is the strip is parallel to y axis. So y equal to phi x to psi x, and then after integration if we put the limits for y, then whole expression will involve only x, means it will become a function of x alone, and then we integrate with respect to x from x equal to a to b, means the strip is then shifted from x equal to a to x equal to b, moved from x equal to a to x equal to b, the whole region is covered. So this is the idea. Integrate along the vertical strip from y equal to phi x to y equal to psi x, and then move the strip from x equal to a to x equal to b, so integral over the whole region is taken, provided the boundaries of the region are like that, y equal to phi x, y equal to psi x, x equal to a, x equal to b. Now if the region D is bounded by continuous curves x equal to phi y, x equal to psi y, and the lines y equal to c, y equal to d, where c less than d and phi y less than equal to psi y, for all y in the interval c less than or equal to y less than or equal to dc. If the region is like that, y equal to c, y equal to d, two lines parallel to x-axis and two curves, one is to the left and one is to the right, x equal to phi y less than or equal to psi y, means x equal to psi y is to the right. So boundaries are like that of the region D. Then in that case we integrate along a horizontal strip with respect to x first, this time x equal to phi y to x equal to psi y. See in the integration, first we integrate with respect to x of the integration function is f of xy, means we take y constant. For the horizontal strip y is constant, thin strip y is constant, so as if partial integral with respect to x, keeping y constant. So after that putting the values up of limits, that is phi y, psi y, everything will become in terms of y, so that will become function of y alone, and then we shall integrate with respect to y from y equal to c to y equal to d, that is the strip will be moved parallel to itself from y equal to c to y equal to d, the whole region is covered, integral over the whole region is taken. So whether we have to integrate with respect to x first or y first, it will depend on the boundary of the region D, or rather it will depend on the way in which we describe the region. If we describe the region by strips parallel to y axis, we have to integrate with respect to y first. If we describe the region parallel to x axis here, then we have to integrate with respect to x first. Okay, so two ways we can calculate depending on the boundary of the region D over which the integral is required. Now we note that order of integration depends, whether with respect to x first or y first, depends on the boundary of the region D, that is whether the region D can be described by strips parallel to x axis or parallel to y axis, as in figure. Here in figure, first figure, and here in second figure. Okay, now if the region D is rectangular, bounded by the lines x equal to a, x equal to b, y equal to c, y equal to d, where a less than b, c less than d, that is the region is a rectangle, then the order of integration is immaterial, means we can integrate with respect to x first or y first, no matter. Thus double integral f of xy over the region D is equal to, here we have integrated with respect to y first, y equal to c to y equal to d, f of xy dy, and then integrated with respect to x, x equal to a to x equal to b, and here it is again we have integrated with respect to x first, x equal to a to x equal to b, f of xy dx, and then integrated with respect to y, y equal to c to y equal to d. Same answer we shall get. So this is because the rectangular region D here can be described by strips parallel to either axis, either by vertical strips or by horizontal strips we can describe it. So two ways we can calculate, but value will be same. Now another observation, for arbitrary shape of D, if the region D has arbitrary shape, it is difficult to calculate double integral, and for circular or elliptic regions sometimes change of variables helps, and that we shall see later. So if the region have boundaries like that in figure 1, two curves, two lines, here also two curves, two lines, and here all are lines boundary, then we can calculate easily. And if the region has boundaries not like these three figures, then it will be very difficult to calculate. And if the boundary is like elliptic or circular, then sometimes change of variables, we shall go to polar coordinates, etc. We shall see it later. Now let us see some examples. Example number 1. Evaluate double integral over d of the function y. Dx dy is there, it is symbol for integration. Here double integration dx dy, where d is the triangular region bounded by the lines y equal to x, y equal to 0, x equal to 1. The boundaries of the triangular region are given. We have to find this double integral. So a rough figure is always necessary. So y equal to x line, this line is y equal to x, making angle 45 degree with x axis. We know slope is 1, and y equal to 0 means x axis, x equal to 1 means this line, x equal to 1. So this is the triangle region, shaded region, and we have to integrate. This integrand is there y. So obviously we see that the region can be described by strips parallel to y axis. So the strip will have its end at y equal to 0 means on x axis, and another end is on the line y equal to x. So limits for y, obviously we see that 0 to x. So the region D can be described by strips parallel to y axis with ends on y equal to 0, that is on x axis, and on y equal to x as in figure, which are to be translated from x equal to 0 to x equal to 1. Here x equal to 0, here x equal to 1. So this strip will be starting from this origin, and it will go up to the line x equal to 1. So strip is to be translated from x equal to 0 to x equal to 1. So therefore this double integral of the function y over d becomes, first to integrate with respect to y along the vertical strip where x is constant, y equal to 0 to y equal to x, and then another bracket is given, integration with respect to x equal to 0 to x equal to 1. So inside integral is y integration is with respect to y is y square by 2, limits y equal to 0, y equal to x we have given here, and then half is taken out constant, and y is x first, upper limit is x, so x square minus y is 0 means 0, so it is only x square. So integration 0 to 1 x square dx, half is outside. So now x square integration is x cube by 3, all of you know, so it is 1 by 3 will be coming. So here 3 and 2 multiplied 1 by 6, and x cube minus x cube, upper limit 1, lower limit 0, so 1 minus 0. So finally we get 1 by 6. This is the answer. Okay. Now example number 2. Evaluate double integration of the function 4xy minus y over the region R. Here symbol is given R, region is R. So R is the rectangular region. What is R? Rectangular region bounded by the lines x equal to 1, x equal to 2, y equal to 0, and y equal to 3. X equal to 1 line, x equal to 2 line, y equal to 0 line, y equal to 3 line we have given. So this is a rectangular region. So the region R can be described by strips parallel to x axis with ends on x equal to 1 and x equal to horizontal strip, which are then translated from y equal to 0 to y equal to 3. Also it can be described by strips parallel to y axis with ends on y equal to 0 and y equal to 3, and translated from x equal to 1 to x equal to 2. So let us first see by taking strips parallel to x axis. Okay, so double integral of the function 4xy minus y over the region R, or the rectangle R, is equal to what? Along the horizontal strip. So x equal to 1 to x equal to 2 horizontal strip. Function is 4xy minus y. Let us integrate with respect to x first, and then integration with respect to y from y equal to 0 to y equal to 3. See, strip, horizontal strip from 0 to 3 we have to go. So first to integrate with respect to x here. X integration is x square by 2, and y constant, so it will be only yx. Now upper limit is y equal to x equal to 1 to x equal to 2. Upper limit is 2. So if we put 2, x equal to 2, so it will be 8. This 4 to cancels 2, and it will be 4 into 2, 8. So 8y minus 2y, and when we put x equal to 1, it will be 1 means it will be 2y minus y, 2y minus y. Okay, and y limit is 0 to 3 with respect to y when we integrate. So finally what we get, 8y minus 2y, 2y minus y, finally we have got 5y with respect to y we have to integrate. So 5 into y square by 2, limit 0 to 3, so 5 by 2 taken out, 9 minus 0, 45 by 2 answer. So we have integrated this along horizontal strip first. Now let us see integration along vertical strip first. So y equal to 0 to y equal to 3 will be limit for y. So the region R can also be described by strips parallel to y axis with ends on y equal to 0 and y equal to 3, which are then to be translated from x equal to 1 to x equal to 2, already taught. Okay, so the double integral of the function 4xy minus y over the region R is given by, now we integrate with respect to y first. So take this y common, taken out, 4x minus 1, y equal to 0 to y equal to 3, and then we integrate with respect to x from x equal to 1 to x equal to 2. So 4x minus 1 is constant, y integration will be y square by 2, limit y equal to 0 to y equal to 3, we should mention here whose limit we are using, and then integration with respect to x. Here 3 square, 9 by 2 minus 0, so only 9 by 2. Okay, now 9 by 2 taken out, 4x integration is x square by 2 means it will be 2x square, and 1 integration will be x. Now if we put upper limit 2 and lower limit 1, so it will be 8 minus 2 minus 2 minus 45 by 2 as before. So answer same, surely answer should be same. Example number 3, evaluate double integration of the function y over the region R, where R is the region bounded by the line y equal to x and the parabola y equal to x square. Line y equal to x square, so y equal to x and the parabola y equal to x square. So let us give the shape figure. Y equal to x square is this parabola we know, and y equal to x is this line. So obviously we see that this region is to be described by strips parallel to y axis. Here lower limit of y is x square, upper limit is x, y equal to x. So the region R can be described by strips parallel to y axis with ends on y equal to x square and y equal to x, which are then to be translated from x equal to 0 to x equal to 1. How we know x equal to 0 to x equal to 1? If we solve this y equal to x and y equal to x square, we get x equal to 0 and 1. Obviously, you see y equal to x square equal to x means x into x minus 1 equal to 0, so x equal to 0 and 1. So this y equal to x and y equal to x square meet at origin and at the point 1 1. So that's why x equal to 0 to x equal to 1. So therefore double integral of the function y over the region R gives us this repeated integrals y equal to x square to x y dy, means integration with respect to y first and then integration with respect to x, limit 0 to 1. So y integration is y square by 2, y equal to x square to y equal to x means upper limit is x, so take half outside, it will be x square minus x to the power 4. When we put y equal to x square here, x to the power 4, and then we integrate with respect to x, it will be x cube by 3 x to the power 5 by 5, 0 to 1. Okay, so it will be half 1 by 3 minus 1 by 5, and when 0 both are 0. Okay, so answer is 1 by 15. So you have got this double integral value. Next, example number 4, evaluate double integral of the function x over the region R. What is R? R is the region bounded by the line y equal to x and the parabola y equal to 4x minus x square. Y equal to x straight line easy, we have drawn. And y equal to 4x minus x square, this is the parabola. Let us solve first these two. So from 1 and 2 we get, putting y equal to x here, we have got simplifying x equal to 0 and x equal to 3. So when x is 0, y is 0. When x is 3, y is also 3. So the line and the parabola meet at origin and 3 comma 3. And y equal to 4x minus x square, it is minus x square. That's why it is concave down. So the figure is roughly we have given like that. So this is the parabola y equal to 4x minus x square. And this is the region R as given in the question. R is this region, shaded region. Now we see that this region can be described by strips parallel to y axis with ends on y equal to x and y equal to 4x minus x square. Okay, and then this strip is to be translated from x equal to 0 to x equal to 3. So that's why the double integral is given like that. Double integral of x over the region R is equal to, first we integrate with respect to y, y equal to x along the strip to y equal to 4x minus x square mentioned. So integration with respect to y first, and then we integrate with respect to x from x equal to 0 to x equal to 3, because strip is to be translated from 0 to 3. Okay, so x integration is x is constant when we integrate with respect to y, so it will be just xy. So x taken out, we have limits for y, so y upper limit 4x minus x square, lower limit is x. So if we put 4x minus x square minus x, then if we simplify, we get 4x minus x 3x, so 3x square when x is multiplied minus x cube. Now we integrate with respect to x, it will be x cube by 3, means only x cube will be coming here, x to the power 4 by 4, 0 to 3. So 3 cube 27, 3 to the power 4 81 by 4 minus 0. So 27 by 4 finally. Answer. Example number 5. Evaluate double integration of the function cos of x plus y over the region D, where D is the domain enclosed by x equal to 0, y equal to pi, y equal to x. So let us draw the figure first. What is the region? Region is x equal to 0 means y axis, y equal to pi means this is the line parallel to x axis, y equal to pi, and y equal to x, this line, making angle 45 degree with x axis. So this is the triangular region. So the region or domain D can be described by strips parallel to y axis. We see that, sorry, parallel to x axis here, as in figure, parallel to x axis, not y axis. We have written it should be x axis, parallel to x axis with ends on x equal to 0 and x equal to y, x equal to 0 and x equal to y. See, horizontal strip, one end is x equal to 0 means on y axis, another end is on line y equal to x, but here limit for x will be x equal to y, 0 to y, and then this strip is to be moved or translated from y equal to 0 to y equal to pi. So the double integral cos of x plus y over the region D becomes integration cos of x plus y with respect to x first, x equal to 0 to x equal to y, and then integration with respect to y from y equal to 0 to y equal to pi. So cos of x plus y integration with respect to x is sine of x plus y, and limit here x 0 to xy. So if we put xy means 2y, sine 2y minus sine y. Okay, now sine 2y integration is minus half cos 2y, all of you know, and minus sine y integration is plus cos y with respect to y when we integrate. And limit 0 to pi means y is pi, y is 0 here. So if we put pi first, so minus half cos 2 pi plus cos pi, and then minus half cos 0 plus cos 0. Okay, so cos 2 pi is 1, cos pi is minus 1, and cos 0 is 1, cos 0 is 1. Okay, so finally we have got minus 2. So the integral is minus 2. Value of the integral is minus 2. Go. Example number 6. Now, sometimes one integral can be found only after change of order of integration, because the integrand is special type, we cannot integrate like that. So that's why change of order of integration problem one is discussed here. So question is like that: change the order of integration in the integrals. These two are repeated integrals. Means here in example number 1, we see that first we integrate with respect to y equal to x to y equal to root x, and then we integrate with respect to x equal to 0 to x equal to 1. But question is change the order of integration. Only writing instead of dy dx as dx dy will not serve the purpose. If we change the order of integration, the limits are also generally changed. So let us see number 1. So this repeated integral is actually, we have written detail here, it is f of xy dy dx. Integration is f of x of xy with respect to y first, y equal to x to y equal to root x, and then with respect to x means x equal to 0 to x equal to 1. So this repeated integral can be written as double integral. So back we are writing, generally we do double integral to repeated integral. Here we are writing repeated integral to double integral. So it is double integral over the region D of the function f of xy, where dx dy can be written as dA, where D is the region bounded by the curves. What curves? Y equal to x, see in the limit y equal to x, y equal to root x, and lines x equal to 0, x equal to 1 here written, which is okay. So y equal to x means this is the line y equal to x. Y equal to root x means y square equal to x. Y square equal to x is parabola. This parabola is y square equal to x. Okay. So as given in the question, first we have to integrate with respect to y, means we have to describe integrate along vertical strip first. So what is written? The region D is described by strips parallel to y axis with ends on y equal to x and y square equal to x. Why y square equal to x? Actually from y equal to root x we get the curve y square equal to x. So y equal to x to y equal to root x. See in the figure, strips parallel to y axis, which are then translated from x equal to 0 to x equal to 1. So vertical strip. Now we want to change the order of integration, means we want to describe the same region by horizontal strips parallel to x axis. And the same region D can be also be described by strips parallel to x axis with ends on, see for the red strip here, horizontal strip, end will be on x equal to y square equal to x equal to y square, all the same. So one end is x equal to y square and another end is on x equal to y. So which are then translated from what? From this origin, means y equal to 0. Here y equal to 0 to y equal to 1. Y equal to 1. Why? If we solve this y equal to root x and y equal to x, we get y equal to 1, x equal to 1. That's why. Okay. So therefore this repeated integral 0 to 1 x to root x f of x y dy dx is equal to double integral. Already we have written. Now this double integral we can integrate like that as repeated integrals along, first integrated along horizontal strip, x equal to y squared to x equal to y squared to x equal to y. So it is not x, it should be y. Okay, correction. See, x equal to y square to x equal to y, other end is x equal to y. So here also, and then y equal to 0 to y equal to 1. That means, and here we have written dx dy, means we have to integrate with respect to x first. So as given in the question, we can write it 0 to 1 and here y squared to y, not y squared to x, it is y squared to y, y squared to y, f of xy dx dy, means with respect to x first and then with respect to y, which is required change of order of integration. So it was dy dx, here we have got dx dy, but see the limits are changed. Here limit for y was x to root x, here limit for x is y squared x or y squared to y, and limit for x was 0 to 1 and limit for y is 0 to 1. Of course these two remain same. Okay. Number 2 is this, minus 1 to 1 0 to root over 1 minus x square f of xy dy dx, means we have to integrate with respect to y first as given. So we have written y equal to 0 to y equal to root over 1 minus x square, and minus 1 to 1 means here x equal to minus 1 to 1 dy dx. That repeated integral we can write as double integral f of xy dA over the region D. What is D here? Now let us see. Where D is the semicircular region above x axis bounded by the circle x square plus y square equal to 1. See, when we write y equal to root over 1 minus x square, so if we square it we get x square plus y square equal to 1. So circle y equal to 0 to that means it is y positive here, so that's why above x axis. So semicircular region above x axis bounded by the circle x square plus y square equal to 1, center origin radius 1, which is described by strips parallel to y axis as given, because with respect to y integration is first here. Strips parallel to y axis with ends on say x axis, y equal to 0 to the circle. In the circle y equal to root over 1 minus x square. Now, and which are then translated from what to what? Minus 1 to 1. See, for the circle left side is here x equal to minus 1 and up to x equal to 1. So strips, vertical strips shifted from my x equal to minus 1 to x equal to 1. The whole region is covered. So this is repeated integral, double integral. Okay, integrated with respect to y first. Now this region D can also be described by strips parallel to x-axis, because we want to change the order of integration. So by red strip parallel to x-axis with ends on what? See in the figure, with end on circle, here also on the circle. So in the left side x will be minus root over 1 minus y square, and the right side x will be root over 1 minus y square, because x square plus y square equal to 1. So from this we can get x square equal to 1 minus y square. So x equal to plus minus root over 1 minus y square. So minus will be in the left, plus will be in the right, means values of x minus root over 1 minus y square and root over 1 minus y square. So endpoints of the horizontal strips are like that. X equal to root over minus root over 1 minus y square and x equal to root over 1 minus y square. And then they are translated, means the strips are translated. They are translated from y equal to 0 to y equal to 1. See, y equal to 0 to y equal to 1. Radius of the circle is 1. So horizontal strip will move from 0 to 1, x-axis to up to y equal to 1 line. And thus the change of order of integration is in this page. Let us see this repeated integral given in the question, and this is equal to double integral over dA. Now we describe it by strips parallel to x-axis. So x equal to minus root over 1 minus y square to root over 1 minus y square, f of x y dx dy. Here we integrate with respect to x first, dx, and then with respect to y limit 0 to 1, already discussed. And instead of this y equal to x equal to, you can write like that as in the question. So which is required? Change of order of integration. Now let us apply this in solving at least one problem. Evaluate integration 0 to infinity 0 to x of the function what? X e to the power minus x square by y dy dx. Means we have to integrate with respect to y first as given in the question. Okay, so this integral is actually x equal to 0 to infinity, y equal to 0 to x, and function is x e to the power minus x square by y dy dx. Means with respect to y we have to integrate first. But see, e to the power minus x square by y we cannot integrate, not known to us. E to the power minus 1 by y, if it is x is not there also, if minus 1 by y we cannot integrate with respect to y. We can integrate e to the power x, e to the power y, e to the power minus y like that. E to the power minus 1 by y we cannot integrate. Okay, so let us try by changing the order of integration. Okay, why? Because we can integrate this function with respect to x. This x square, if we put t, twice x dx will be coming, so x is here, so we can integrate with respect to x. That's why let us change the order of integration. So this repeated integral we have written as double integral over the region D. What is D? D is the region in the first quadrant below the line y equal to x. How we understand? See, y equal to 0 to y equal to x. So y equal to x line we have drawn. This is y equal to x line, and strip is y equal to 0 to y equal to x. So this is the vertical strip, and then x equal to 0 to infinity means what? This vertical strip is to be translated from x equal to 0 to infinity. So this is as given. Now we cannot integrate with respect to y first, so we want to integrate with respect to x first. Means we want to describe this region by horizontal strips, this red strip. So this region D can be described by horizontal strips with and C on what? On x equal to y. X is equal to y, left end of this strip, and right end is goes up to infinity. And then the strip is to be moved from y equal to 0 to what? Above. It will go up and up, it will go up to infinity. Okay, so see what is written. Changing the order of integration. X equal to y to infinity for the horizontal strip, and then the strip is to be moved from y equal to 0 to y equal to infinity. And now here we have written dx dy. This time we have to integrate with respect to x first. Now we can integrate. Why? X square by y, let us put it t. Y is constant when we integrate with respect to x, y constant. So x square by y equal to t. So twice x by y dx will be dt, means x dx will be half y dt. So x e to the power minus x square by y dx becomes what? Half y e to the power minus t dt. Half x dx is half y dt, and y taken out because constant when we integrate with respect to x or t here. And then we get minus half y e to the power minus t, means minus half y e to the power minus x square by y. So this value directly we have taken here. Okay, side calculation is there. So minus half y e to the power minus x square by y, and limits for x equal to y to infinity. Now when we put infinite, of course infinity is to be used always in limiting sense. So when we take limit as x tends to infinity, e to the power minus x square by y is x equal to y to x equal to infinity. Okay, so e to the power minus infinity will be coming. When x tends to infinity, this is e to the power minus infinity coming, but in the limiting below that we know is 0. Okay, so that's why it is 0 taken, and then when x is y, y square by y will be e to the power minus y. So easy answer. Half is taken out. When lower limit is substituted, another minus sign will be there, so plus. Okay, so half integration 0 to infinity y e to the power minus y dy. Now this we can do by integration by parts. First function y, second function e to the power minus y, integration with respect to y will be minus e to the power minus y. Okay, 0 to infinity, minus derivative of first function, derivative of y with respect to y is 1, and then integration of second function is again minus e to the power minus y. Okay, and then when we take infinity, means limiting value, when y is infinite, so e to the power minus infinity limiting, that value is 0, limiting value is 0, and when 0, y is 0, so 0. And here we got minus minus plus, and e to the power minus y, again integrate, if we integrate it will be again minus e to the power minus y. Okay, and when we take infinity, means limiting value, limit e to the power minus y, y tends to infinity is 0. So and when y is 0, it will be 1. So what you get, 0 plus 1, minus minus plus, already there is a minus sign. So finally we have got half. See, we have integrated, we are successful in finding this repeated integral by changing the order of integration. That is the utility. Okay, so the evaluation is possible only due to application of change of order of integration, that is describing d by strips parallel to x-axis. In the figure it was read, from x equal to y to infinity and translating them from 0 to infinity. So this is the utility of change of order of integration. So thank you for today.